Today, we're going to dive into one of the deepest, weirdest, and most mind-bending mysteries in all of science. It's what Albert Einstein himself famously called spooky action at a distance.
So let's start with a question that seems to break the most fundamental rule in the entire universe, the speed of light. I mean, how is it possible that two things, even if they're on opposite sides of the galaxy, can be so connected that a change in one is instantly, and I mean instantly, felt by the other? This isn't just a fun little puzzle. It literally challenges our whole idea of what reality is.
All right, to get to the bottom of this, we have to investigate a kind of crime scene. Not a real one, of course, but a legendary thought experiment first dreamed up by Einstein and his colleagues, and then polished up by a physicist named David Bohm. This is where the whole mystery really kicks off.
At the heart of this experiment, you've got a pair of what are called entangled particles. The easiest way to think of them is as cosmic twins. They're born from a single event, and because of that, they share this incredibly special connected state. It's like they were born from a single coin that was magically split in two. If one half is heads, the other half has to be tails. Their fates are linked. Forever.
Now, the setup itself is actually pretty simple. You have a source that spits out our two twin particles, and they go zooming off in opposite directions. They could travel for light years. It doesn't matter. Then, one physicist, let's call her Alice, she measures a property of her particle, particle A. The exact moment she does that, something completely unbelievable happens to particle B, which could be all the way across the universe with another physicist, Bob.
And here's the truly wild part. Here's what Bob discovers. If Alice measures her particle spin and gets up, Bob's particle at that very same instant will always be down. If she gets down, he gets up. And this happens every single time. It's a perfect anti-correlation, and there's no delay. It's instantaneous.
And that right there, that's the spooky action that drove Einstein crazy. The standard model of quantum mechanics just kind of shrugged and said, yeah, that's non-locality. That's just how the universe is. But for Einstein, this was a huge red flag. It meant the theory had to be missing something big.
Right, so Einstein and his buddies, they just couldn't accept this spookiness. It felt wrong. So they came up with a much more intuitive, common-sense solution. They pointed the finger at an obvious suspect that would solve the whole mystery without having to break the cosmic speed limit.
And their big idea is called local realism. It sounds a little academic, but it's really just two common-sense rules we all live by. First, local, which just means nothing can travel faster than light. And second, realism, which says that things have definite properties, like being spin up or spin down, even before we bother to look at them. To Einstein, this meant quantum mechanics wasn't spooky, it was just incomplete.
And this analogy is just perfect for explaining their point. Imagine you have a pair of gloves. You put the right glove in one box, the left in another, and mail them to opposite ends of the earth. When your friend opens their box and sees a right-handed glove, you instantly know you have the left-handed one. There's no spooky communication between the boxes. The information, which glove was set from the very beginning. Einstein argued the particles were exactly the same. They carried hidden instructions from the moment they were born.
And you know what? For decades, this hidden instructions idea seemed like the most logical answer. It was just a philosophical debate, though. There was no way to actually test it. Well, that was true until a brilliant physicist named John Bell came along and figured out a way to put reality itself on the witness stand.
Yeah, it took nearly 30 years, but in 1964, Bell found a way to drag this whole debate out of the philosophy department and into a real, actual lab. He figured out how to ask the universe a direct question. Do you follow Einstein's common sense rules, or are you really as spooky as quantum mechanics says you are?
Bell's theorem is honestly a stroke of genius. He basically showed, using math, that if the universe is based on local realism, if those hidden instructions are a real thing, then there's a strict limit on how correlated the measurements on those two particles can be. You can think of it like a speed limit for common sense.
So here it is, the crucial point. When scientists finally did the experiments, and they have been done over and over and over again since the 70s, the results were an absolute bombshell. Reality consistently and by a lot violates Bell's limit. It smashes right through that common sense speed limit. What that means is that Einstein's obvious suspect, those hidden instructions, had a rock-solid alibi. It couldn't be the right answer.
And this is where things just get completely bizarre. If local, common-sense reality is off the table, what are we left with? We are forced to admit that the universe is, on some fundamental level, non-local and deeply, deeply weird.
And this leaves us with a lineup of new suspects that are way stranger than anything Einstein proposed. So, with Einstein's nice, simple explanation totally rolled out, physicists had to get really creative. And that leads us to the remaining possibilities, which are all mind-bending interpretations of what quantum mechanics is actually telling us about the nature of reality.
Okay, so this chart kind of breaks down the main contenders. First up are collapse theories, which basically say, yep, it's real spooky action. Measuring one particle literally causes an instant change in the other. Then you have something like Bohm's theory, which suggests there's a hidden guiding field that connects everything in the universe. And then you have maybe the wildest idea of all, the many worlds interpretation. This one says that every possible outcome actually happens, just in its own parallel universe. The correlation we see is just our own limited perspective from one branch of reality. Wild, right?
Now, when you hear all this talk about instantaneous connections across the galaxy, your brain probably jumps to one very exciting question. If we can affect something instantly, no matter how far away it is, can we use this to build a faster-than-light communicator?
I mean, could we, in theory, build a Bell telephone? Could Alice wiggle her particle around to send a Morse code message of ups and downs to Bob on the other side of the galaxy instantly?
The answer, and I'm sorry to break this to all the sci-fi fans out there, is a big, resounding, definite no. And there's actually a very elegant reason for it.
It all comes down to something called the no signaling theorem. Here's the catch, and it's a huge one. Even though the correlation between the particles is perfect, the actual outcome Alice gets when she measures her particle is completely 100% random. She can't force her particle to be spin up to send a 1 to Bob. The universe gives her a totally random result, 50-50 chance. And while Bob's result will instantly be the opposite, neither of them can actually control their end of the line to send a meaningful message. It seems the universe protects cause and effect, even when it's being spooky.
So, where does all this leave us? We're left with a reality that is far stranger and more deeply interconnected than our everyday intuition can possibly handle. No, we can't build an instant telephone, but we've proven something maybe even more profound. The universe is fundamentally non-local. Our common sense, it fails us here. And it forces us to ask this incredibly deep question. If two things can be linked instantly across the entire cosmos, what does that really tell us about the nature of space, time, and reality itself? The investigation is far, far from over.